Dear students, in the previous class we have discussed instrumental variable estimation in the case of multiple linear regression model. In the model it was assumed that there is only one endogenous explanatory variable y2 along with the one IV for y2. y2 is endogenous explanatory variable and z2 is the instrumental variable for y2. But it often happens that we have more than one exogenous variable excluded from the structural model. More than one explanatory variable excluded from the structural model and might be correlated with the y2, which means that these these exogenous variables excluded from the model are valid IV for y2. That means instead of z2, for y2, suppose that we have z2 and z3 or z2, z3, etc. excluded from the equation. In that case, this z2 is a valid IV for y2. z3 is also a valid IV for y2. Now we have to see how to estimate instrumental variable regression model if there are more than one IV for an endogenous explanatory variable. We use what is known as the two-stage least squares. Two-stage least squares, 2SLS. To explain how the instrumental variable method works, we start with a single endogenous explanatory variable. We start with a single endogenous explanatory variable. That is, our model is y1 is equal to beta 0 plus beta 1 y2 plus beta 2 z1 plus u1. Single endogenous explanatory variable. That is, y2 is endogenous, means correlated with u1. z1 is exogenous, uncorrelated with the u1. Suppose that we have two exogenous variables z2 and z3 excluded from this equation. z2 and z3 excluded from this equation. Our assumption is that z2 and z3 do not appear in equation 1. z2 and z3 do not appear in equation 1 and are uncorrelated with the u1. And are uncorrelated with the u1. z2 and z3 should not appear in equation 1 and z2 and z3 are uncorrelated with the u1. And this condition is known as exclusion restrictions. Exclusion restrictions. That is, z2 and z3 are excluded from equation 1. Now, if z2 and z3 are both correlated with y2, then we could use z2 as IV for y2, z3 as IV for y2. z2 alone as IV for y2, z3 alone as IV for y2. But then we have two IV estimators, z2, z3. Then we have two instrumental variable estimators, one using z2 the other using Z3. And in general, neither of it is efficient. In general, neither of it is efficient. And since each of Z1 and Z2 and Z3 are uncorrelated with the U1, Z1, Z2 and Z3 are uncorrelated with the U1, any linear combination is also uncorrelated with the U1. So that we can use a linear combination of Z1, Z2 and Z3 as a valid IV for Y2. Z1 is uncorrelated with the U1, Z2 is uncorrelated with the U1, Z3 is also uncorrelated with the U1. So we can use a linear combination of Z1, Z2 and Z3 as valid instrumental variable for Y2. So to find the best instrumental variable, we choose a linear combination which is most highly correlated with Y2. Most highly correlated with Y2. And this is given by the reduced form equation for Y2. Y2 is equal to pi 0 plus pi 1 Z1 plus pi 2 Z2 plus pi 3 Z3. So the best linear combination for Y2 is given as the reduced form equation for Y2. Y2 is a linear combination of Z1, Z2 and Z3 plus V2. Y2 is a linear combination of Z1, Z2, Z3 and V2 with the expected V2 equal to 0. Covariance Z1 V2 0, covariance Z2 V2 0, covariance Z3 V3 0. So the best IV for Y2 is the linear combination, and let us call this linear combination Y star 2. So Y2 is equal to Y star 2 plus V2. This Y star 2 is this part, Y star 2. So Y2 is equal to Y star 2 plus V2. So we say that and as we have stated earlier, the instrumental variables for Y2 are Z2 and Z3. Also, Z1 is also present in the equation. And for this IV not to be perfectly correlated with Z1, we need at least one of the pi 2 or pi 3 not to be equal to 0. If both of these are equal to 0, pi 2 and pi 3, then Y2 and Z1 are perfectly linearly related. Then estimation is not possible. So we require pi 2 not equal to 0, pi 3 not equal to 0. That is to ensure that Y2 and Z1 are not perfectly linearly related. And this is the key identification condition, that we assume that all Zj are exogenous. So the identification condition is pi 2 not equal to 0, pi 3 not equal to 0. And we can test this using the F test. Since we have to test two coefficients, we use the F test to test the requirement that pi 2 is not equal to 0, pi 3 is not equal to 0. Now, a useful way to think of equation of equation 2, that is this equation. A useful way to think about this equation is that y2 is divided into or decomposed into two parts. One is y star 2, that part of y2 not correlated with the u1. y2 is correlated with the u1, that is the problem. Then y2 is y star 2 and v2. Now in this specification, y star 2 is a linear combination of exogenous z1, z2 and z3. So this part is not correlated with the u1, y star 2. Then the other part v2 is correlated with the u1. v2 is possibly correlated with the u1. That means y2 is endogenous here because v2, a part of y2 is correlated with the u1. This we can test. We can test this possibility that we will discuss later to see whether the instrument is endogenous or not. But remember this, we cannot apply this because this is a population concept. So what we do is, if you have a data, we regress y2 on z1, z2 and z3, you will get y hat 2 as equal to y hat 0 plus y hat 1 z1 plus y hat 2 z2 plus y hat 3 z3 if we have a data. So y2 become y hat 2 plus v hat 2. Instead of y star 2 and v2, we have y2 is equal to y hat 2 plus v hat 2. And y hat 2 is given by this. And v hat 2, the estimator of v2. Now, and once we have y hat 2 obtained in this way, then we can use it as an IV, instrumental variable for y2, and the three equations can be solved to obtain the IV estimators. That is, y2 is replaced by y hat 2. The first equation is sigma y 1i minus beta hat 0 minus beta 2 hat y 2i minus beta hat 3 z 1i equal to 0, I is equal to, then sigma z 1i y 1i minus beta hat 0 minus y 2i minus beta hat 3 z 1i is equal to 0. Sigma y hat 1 2i into y 1i minus beta hat 0 minus beta hat 2 y 2i minus beta hat 3 z 1i is equal to 0. So instead of using y2, we use y hat 2, and solving this you will obtain the instrumental variable estimators of beta hat 0, beta 2 hat and beta 3 hat. Now we can show that if since y1 is equal to beta 0 plus beta 1 y2 plus beta 2 z1 plus u1. y1 can be written as beta 0 plus beta 1 y star 2 plus beta 2 z1 plus u1 plus beta 1 v2, substituting the value of y2. We will get the equation like this. Now the error term now is u1 plus beta 1 v2. It is a composite error term. It has zero mean and is uncorrelated with the y star 2. Now the composite error term is this, and this composite error term has zero mean. It is also not correlated with y star 2 because y star 2 is a linear combination of non-stochastic z's or exogenous z's. So this is the theory behind 2SLS. And remember this, most of these software packages I suggest you use have special commands to estimate 2SLS. You need to specify only two things: dependent variable, list of all explanatory variables, and the list of all the instrumental variables, that is all the exogenous variables. There is no need for estimating this in two steps. There is no need for estimating y hat 2, etc. All these will be performed by the software. Software will tell you what is, you just give the endogenous variable, then all the explanatory variables, exogenous and endogenous. Then the list of instruments. Instruments means all the exogenous variables. The computer will give a direct estimates. Now, in a model, now consider the model y1 is equal to beta 0 plus beta 1 y2 plus beta 3 z1 plus beta k zk minus 1 plus u1. And in this multiple linear regression model, if there is only one IV for y2, say zk, one ID for one IV for y2, then this model, that is the estimators, are identical to 2SLS. Estimators will be identical to identical to 2SLS, two-stage least squares. And so when we have one IV for each endogenous explanatory variable, we can call the estimation method IV or 2SLS. If there is one IV for each endogenous explanatory variable, we can say we can use IV or 2SLS. IV or 2SLS. Both will give you identical results. We use 2SLS when there are more than one IV for an endogenous explanatory variable. In that case, we take a linear combination of all the exogenous variables as IV for this endogenous explanatory variables. Endogenous explanatory variable, that is what we do. So this is two-stage least squares with one endogenous explanatory variable, one endogenous explanatory variable, and more than one instrumental variable. In the next class, we will generalize it to multiple endogenous explanatory variables. multiple endogenous explanatory variables. So to summarize, in the model, it is assumed that Z1, Z2, etc., Zk minus 1 uncorrelated with the U1. We need at least one exogenous variable not included in this equation. One exogenous variable not included in this equation, but partially correlated with the Y2. Remember, partially correlated with the Y2. That is, after keeping constant Z1, Z2, that is in the first stage. Then the estimators so obtained will be consistent. Then the usual 2SLS standard errors, T statistics, etc. are valid asymptotically. And for this, we need one more assumption, that is homoscedasticity of U1 is required. For time series applications, there are other assumptions, etc. that we will consider later.